Hello, and welcome back to the Machine Learning at Microsoft YouTube channel. Today is another one of those paper review calls. Today we have Karol Zak, who is a machine learning engineer from Microsoft Poland. He's one of my partners in crime. We've worked on so many projects together, and Karol is pretty much our worldwide expert in semantic segmentation. Today he's talking about a paper called UNet, Convolutional Networks for Biomedical Image Segmentation. And this paper introduced a new architecture for doing semantic segmentation, and it was significantly better than what came before that, because before then, most of the approaches were using kind of sliding window convolutional neural networks. So this is a significant departure from that, and the architecture itself is fascinating. We talk about it on the call. It has a U shape, and the encoder part of the network sort of transforms the information into a compressed spatial domain, but still in the spatial domain with a large depth of convolutional layers. And then the up convolutional part of the network transforms it back into the not quite the original space, but there are skip connections from the encoder layer. So it's absolutely fascinating. We spend about sort of 10 or 15 minutes just kind of meditating on the architecture. Anyway, it was a fantastic call. It went on for about 90 minutes because this was quite unique, because Karol started off quite academic, talking about the paper and the contributions, but then he moved on at the end to talk about some of the practical implementations that he's done, some of the projects that he's worked on, and also he's got this amazing GitHub repo where he's posted some of his kind of helper libraries and stuff, especially using Keras online. So without any further ado, I hope you enjoy the call, and we'll be back next week with a really interesting talk on adversarial examples with Katia Mustafina. Thank you very much.
Okay, guys. So, hello, welcome everyone. My name is Karol Zak. I'm a machine learning software engineer at commercial software engineering at Microsoft. First off, I'm super excited to be talking about this this particular research paper, because I'm very, very excited about it. I'm very passionate about it, and it's like Tim mentioned, it's very close to my heart. I did a couple of projects using this this state-of-the-art architecture to solve some really cool tasks. And then, yeah, I would love to share with you some of the learnings and especially the details of this research paper. So the full title is UNet Convolutional Networks for Biomedical Image Segmentation. But before we jump straight into the paper itself and discussing the details of this paper, I'd love to first do a kind of introduction to what kind of visual recognition task we can be seeing in a computer vision area of machine learning. And so first, and I guess the most simple one, is image classification, where we basically try to retrieve an information what is in the image, what is presented in the image. So in this example, coming from Microsoft Cocoa research paper, we can see that in this upper left corner image, we got person, sheep, and a dog. The problem is that we don't exactly know, we have no idea where are these located, how many of these instances we have in the image, and so on. And that's why later on we introduced something called object localization or object detection, which not only tells us what is in the picture, in the image, but also where is it located, which is very, very helpful. But then this This approach gives us only the bounding boxes, the rectangles marking the exact object located in the image, and another let's say deeper level of this visual recognition would be semantic segmentation, which will be the main topic for today's call. And semantic segmentation is basically per pixel classification for images. So we tried with this approach, we tried to mark each pixel of our image with specific label it with specific class. So in this case, as you can see, we have exact locations of each class that we are interested in, like the person, the sheep, and the dog. And there's also one even deeper level of semantic segmentation, which is semantic instance segmentation. So we not only want to know in which places we have pixels representing different classes like sheep, dog, and person, but we also want to know how many of these separate objects, how many instances of each class are presented in this particular image. Like I said, we're going to focus on semantic segmentation, and as for some real-life use cases that you can already see being implemented, there's a lot happening in terms of aerial images, applications of semantic segmentation for aerial images. Like in this case, we're trying to segment out roads, houses, rooftops, probably some green areas as well, and so on. Whereas in this image, for example, we're trying to get information, extract information from images. Where are the crops located on some green fields? And one of the most common use cases as well is for self-driving car, or let's say environment-aware cars, where we basically try to segment out, use semantic segmentation to retrieve information about everything that is presented in the image, like the cars, the persons crossing the road itself, buildings, and so on. But the topic that the research paper, the original research paper for state-of-the-art semantic segmentation architecture is focusing on is application of semantic segmentation for biomedical images. And so you need to know that the original paper comes back from May 2015. That was the first release of this paper. So it's quite old, you can say, especially in terms of machine learning world, because we know that it's advancing quite fast. So it was published back in May 2015, and it was basically, at the time, it was simply the best, and it was state of the art, and it still is state of the art. At the time, it was simply the best. There was, like, in some of the competitions, it was winning them by a really huge margin. So, and as you can read in this abstract, for biomedical images, and especially for visual recognition for biomedical images, there's very few training examples available for models to train. It's specifically because the domain expertise is very limited, and it's hard to get really well labeled images for training. It's a bit easier for very general topics like, dogs, cats, person, and that kind of stuff. But for this kind of very domain-specific images, it's hard to obtain real high-quality data, and that's why for example, the main challenge that they're describing in this research paper only serves you with gives you 30 training labeled training images, just 30 of them, and that's why they came up with this brilliant idea of unit network, and they specifically focused on requirement of a small number of training examples, and they focus on extensive usage of data augmentation to basically to create a more general model. One thing I think already mentioned, like I said, it's still state of the art, even though there were some different architectures that were in some applications performing a bit better than Unit. Still, Unit is the most commonly used for semantic segmentation tasks. The community is quite strong behind it. There's plenty of examples and different implementations and modifications of Unit network. But like I said, the very basic of it is just still state of the art and most commonly used. Right. So maybe before we go into more detail, I will just show you the overview of the research paper. How is it? How the structure looks and that kind of thing, because we're going to go in detail through each topic, each section of this research paper, but let me give you an overview. So it starts, like I said, with the abstract that we already went through, and then goes the introduction, basically describing what was the current best approach and how they, what was the theory behind this specific implementation of unit network. There's also architecture attached that we will go into detail later on. They're also describing the overlap tile strategy, basically how they cropped and how they used the images they were provided with to run the predictions on the model. And of course, after the introduction, there's the network architecture in detail, rights, which we will cover as well, training details like stuff like the loss function, what kind of batch size they used, and optimizer, right, as well. So everything is defined here. They also introduced some custom pre-computed weight map for loss function to basically improve the predictions, improve the separation border between the cells. We're going to get into that later on. So at the end of the training description, they also go into detail of data augmentation techniques that they use. And like I said, they use very extensive data augmentation because they only had couple of images for training purposes. And of course, at the end, they brag about the outcomes and the experiments they performed and how they did perform against some challenges back in 2015 and how they basically rocked them. So we're going to go into more detail later. Right. Back to the slides. As for introductions, the main takeaways from the introduction, I guess, is that they were discussing the previous state-of-the-art approaches, like Tim already mentioned, the sliding windows, convolutional network with sliding windows, which was at the time state-of-the-art solution approach for semantic segmentation. And the way that they used it is quite interesting because they basically prepared patches like local regions around the input pixel that they wanted to predict, to classify, and simply use sliding window technique to classify each pixel. So you can imagine that it was like there was a lot of overhead happening in this approach because they were going through the same data over and over and over again. So not the best approach, but it was the best at the time. They strongly highlighted the need back in 2015. There was a strong need for per pixel classification for some visual tasks. At the time, they were working in biomedical images domain, and especially for that domain, it was required to build some kind of new architecture, new approach to work with this. And of course, small number of training examples. And it was not only for the ISBI challenge, but for most of the biomedical tasks, the number of training images was very, very limited. So they had to come up with approach, a strategy that would be possible to leverage that small number of training examples. Just so you get a better idea of what kind of images they were dealing with, this is one of the examples for ISBI 2015 cell tracking challenge. And on the left-hand side, you get the original image, which is obviously grayscale, and ground truth mask. It's worth to say that in their approach, here, the mask is basically, again, a grayscale. I mean, in this case, it's even black and white image representing the annotated cells from ground truth and also the background, which is black color in this case. Okay, so in the later part of the introduction of this research paper, the authors discussed the theory behind unit architecture and how they leveraged what was available at the time. So they came up with this more elegant, fully convolutional network proposal. And the main idea here was to basically use downsampling path of this architecture for features extraction, and it was supposed to be followed by upsampling path for precise localization of these features in these higher resolution layers. And it's only the theory behind it. Don't worry, we're gonna go through the architecture in more detail because this is the key point of this key takeaway from this paper. Another key idea in this thing is in this architecture is concatenating downsampling feature maps or with corresponding upsampling layers to basically help successive convolutional layers to assemble a more precise output of our segmentation map. And I guess it's gonna give you more idea. Like I said, it's only the theory behind it, but when you see the implementation or the architecture, it will make much more sense. One thing worth mentioning here before we jump into the actual architecture is the overlap tile strategy. And the interesting part is, unlike I guess most of the network architectures I'm aware of, the input is much bigger here than the output size. So we kind of feed more information, more padded information into the input of the network, and we retrieve only the central part. So basically the part with full context, where the full context is available in the input image. It's happening like that because they didn't use any kind of padding in convolutional layers throughout the architecture. So they used the so-called valid padding. And so the output segmentation map only contains the pixels for which the full context is available in the input image. So if you look at this example here, we can see that the blue box here. The blue box here is the input image that is being fed into the network as an input, and this yellow box is what is basically being outputted at the end of the network as a segmentation map, which you can see here as well. So throughout the process of doing the prediction, generating the segmentation map, it's kind of losing or dropping the border information, because that's what's happening when you don't use padding in your convolutional layers. But again, we're going to see more of that and discuss more of that in the following slides. Oh, one more important thing here for the overlap tile strategy. Because as you can see on the edge cases or the border cases of the image, we're kind of missing some information, right? So they basically fix that by basically extrapolating the image using mirroring technique here. So the edge or the border of an image is being mirrored here to be extended into some bigger size, so that we kind of generate some additional information for the network to generate the feature map. Yeah. As for the task that this network was designed for, like I previously said, there was always very little training data available, and for some of the challenges, there were like 20 or 30 images available, labeled images available for training purposes. So they had to come up with very excessive data augmentation strategy, and they did. And very important, or another challenge that they were facing was working on more accurate separation of touching objects, because when you look into these cells here, many of them like they are all a single class, right? And many of them were touching each other, so basically very close to each other. And it's easy for network segmentation network to basically merge those cells to kind of omit this border here. So they had to come up with a solution to penalize the network for doing so, and to focus more on drawing those boundaries, those separation borders between the cells. And one more thing, yeah, so the solution they come up with is completely reusable. I mean, they reuse it for like many challenges, many biomedical images tasks, and the cool thing is, like we already mentioned, it can be used to even in even more domains. Like I previously said, aerial images is very popular to use semantic segmentation there, and this particular network as well, or satellite images, or any other kind of domain. And then going through the network architecture, it's, like I said, it's very well defined here. So it basically consists of a contracting path, which is on the left side, an expansive path, which is on the right side, and then they very well, it's very well defined, and it was very easy to kind of reconstruct the network architecture using some modern tools like Keras, for example. But again, I guess picture tells more than 1,000 words, so I guess we should jump straight to the image representing the overall architecture of U network, and I guess you already can see where the U network name is coming from, because obviously there's a U shape going on over here. On the left-hand side, we got the input of our network. On the right-hand side, we got the output with segmentation map. So the left-hand side part of this network here, this is the so-called downsampling part. So basically the part where we are running the image through to multiple convolutional layer blocks. Then we're adding some max pooling to kind of do the downsampling to reduce the size of the image or the patches, and we're increasing the number of layers by basically doubling the number of filters for convolutional layers on each convolutional block or each layer of unit that we are using here. And so this is the.
So Karol,
yeah.
I think we should spend about a minute just meditating
we will,
on this image, because this image is absolutely wonderful. Because it seems to be on the left-hand side kind of transform, because most convolutional neural networks, they transform the data in the encoder, they transform the data out of the space domain, out of this kind of sparse, statistically undescriptive space domain. But this one doesn't flatten it. So it's still spatial. So even when it comes down on the left-hand side, it goes down to about 30 or even 28 squared, but with still quite a large depth. So I think on the one from the bottom, that it has the response map has a depth of 512 layers, which is insane. And then we do this up convolution, and then the final output size in this particular case has a depth of 2. So it has kind of like a probability for every single pixel for 2 classes. And then we have these kind of skip connections, don't we, which seem to maintain some of the spatial information, but it's almost as if by downsampling into a smaller space domain, we're learning kind of global spatial dependencies, but the skip connections allow us to increase the location specificity after we've upsampled. It's really clever, isn't it, what's going on?
It is. It's clever and beautiful. It's beautiful. I love it, and like you said, it's very, very clever. And as you mentioned, on the left-hand side, on the downsampling path, there's basically feature extraction happening here, and as you mentioned, we're reducing the size of the patches of images or the images, and we're kind of increasing the depth, and like I said, we're basically doubling on each layer of unit. We're doubling the number of layers here, and there's no flattening here or flattening. There's no fully connected layer as well. It's fully convolutional from start to end. And as you mentioned, even the last layer here, it's 1-by-1 convolution.
Yeah, it's interesting to meditate on that as well. So 1-by-1 convolution, you might think, well, what does that do? But it's a way of reducing the depth map down. So we're reducing from 64 to 2, but we're maintaining the spatial dimension. So the spatial domain stays the same. And also it might be worth meditating on what up convolution means.
Yes, we will.
It's because it's kind of the same as convolution, but you do this kind of padding and striding.
So I already said that, but just to be more specific, on the left-hand side, we got the contractive path or the downsampling path to basically capture the context of the images of what we're looking at. And then we got the symmetric expanding path or the upsampling path for precise localization of these features of these contexts, right? So if we go here, we can discuss in detail what's happening on the left-hand side and right-hand side of this architecture. So in principle, the vanilla unit architecture is 4 convolutional blocks with 2 convolutional layers each, followed by max pooling 2-by-2 with striped 2 layers used for downsampling, which was already mentioned by us. And then there's the fifth block. So we got first block here with two convolutional layers, second max pooling, then another two convolutional layers, max pooling, another two convolutional layers, max pooling, another two convolutional layers, and max pooling, and it's followed here by another two convolutional layers. But as you can see here, we're not doing max pooling anymore here. We're doing upsampling, which we will go into detail a bit later. So the total number of convolutional blocks, convolutional layers for this architecture is 23 for vanilla unit. And the important thing here is that first convolution block is using 64 filters on each convolutional layer, and then on every consecutive convolutional block is basically doubling the number of filters until we get to like 1024 here at the bottom. Right, so the principle, the basic principle here is to reduce the resolution and increase the depth. So basically the number of layers. We're not using any padding, so we're kind of losing the border information with each convolutional layer here. Like you see here, the input image is 572 by 572, and then it's basically losing a bit of border edge information here. Max pooling is basically dividing the size by 2 every time. No big surprise here. And also throughout the whole network, they're using 3x3 filters with ReLU activation, which is presented here in comparison to sigmoid activation. And I guess ReLU is basically most popular in terms of convolutional layers. Correct me if I'm wrong, Tim.
Oh, absolutely. No one would ever use sigmoid ever. apart from at the very end of the network.
Yeah,
it's just worth pointing out as well that the output resolution is smaller. So presumably the authors would have cropped or resized the labels that they were training then, because the input image would be that image that you showed us, which had the mirror padding around the edge, and then the label would have been, presumably for every pixel it would have been a 1 or a 0 for the two respective classes that they were predicting.
Yes, correct. Very much correct. And as you already mentioned, they use two classes. So one class representing the actual cells and the second class representing the background or the borders. But it's possible to use as many classes as you like. And so you might have like 10 or 20 or 80 layers here. But I have to tell you that in most of the cases I've seen so far, especially I'm following some of the Kaggle competitions and some of the entries there, people usually build separate models, separate unit models for each class they want to predict, basically.
Oh, that's very interesting. Could I make another comment as well? So, because you were saying that one of the unique strengths of this architecture is that it can be trained. I mean, another comment that I don't think we've made is that, first of all, it can be trained with a large input size. And most of the time with convolutional neural networks, we actually have to have quite a low input size. We typically use 100 squared or 200 squared. So this is up in the 500 squared, which is incredible. But also, when we look at all of these convolutional layers and deconvolution, up convolution, presumably UNet has millions of parameters. I mean, let's say 30 million parameters. So does that imply that does that imply that it doesn't work well with a small training set? It's only because of the augmentation that it works well, or does it work well with a small training set regardless of augmentation?
I mean, augmentation is important to avoid overfitting. But I guess they favor bigger or higher resolution image over higher or bigger or smaller images with bigger batch size, and it so positively.
Yeah, my understanding is augmentation isn't about reducing overfitting. It's about preventing it from learning features that you don't want to learn. And so in that sense, it helps because then all the nodes in the network focus on what we actually want it to learn, which presumably is generalizable. For example, all the rotations and whatnot, but you're just copying what data is there. So you're not really, yeah.
It's kind of both. Augmentation is primarily for reducing overfitting, but it's also for that, Keith. Yeah, the main reason we do augmentation is to reduce overfitting.
Okay.
Yeah, because there's always a kind of relationship, isn't there, between how big your data is and how big your model is. And, because there should be a kind of parsimony, that the model should be kind of smaller than your data, because otherwise the model will just learn your data perfectly. So that there's an augmentation, of course, is a way of making your data bigger than your model, because in almost all commercial cases of deep learning, we have this problem that we don't have enough data. It's the perennial problem. So therefore, overfitting is the perennial problem.
Yeah, sure. But you can increase data size arbitrarily without actually increasing the information content of the data. And augmentation doesn't increase the information content of the information that comes from the data, right? We're introducing information, rotation, scaling, translation, whatever. So we're basically telling it things that we don't want it to learn. Like we don't want it. Or rather, we want it to learn to ignore, rotation, translation, scaling, yada.
Not necessarily. I mean, it depends on the case, but especially in case of these biomedical images, the rotations and that kind of transformations are very much realistic, and that's kind of the transformation we can expect.
We want it to ignore that for the purpose of classification. Like if I rotate a class, I don't want the class to change.
It's kind of interesting, though. It's a philosophical question whether you are giving it new information or not, because the neural net, as you know, CNNs are not rotationally invariant, which is why augmentation, we do rotations. But as far as the network is concerned, it's learning something completely new. But as far as we're concerned, it's not new information, is it? So I'm not quite sure how to describe that.
Yeah, understood.
Right. But that's very interesting how we can leverage the augmentation, especially in that kind of scenarios. But going back to
one final philosophical point, just on what Tim had said much earlier in the conversation. It's interesting. This UNet is almost perfectly symmetric, but it has this very interesting asymmetry, which is the skip layers. Right. And just in my sort of prior or previous decades or whatever, I've noticed that a lot of times some of the most interesting science happens when you have these things that are almost symmetric, but there's one little different thing. Like consider Maxwell's equations and, the difference between E field and B field. There's one little asymmetry there, and it makes all the difference,
That is fascinating, and one thing that you kind of prompted me. That's the thing. That's why I kind of said we should just meditate on this image for ages, because every time I look at it, I notice something different. And these skip connections, what they do is they concatenate in the depth domain, not in the spatial domain, which is why if you look at this 200 squared thing in the middle on the right hand side, of course the depth has now jumped up to 256 because the previous response maps from the other side of the network get concatenated in the depth domain, and of course there is an asymmetry on the resolution on the output. It's absolutely fascinating how this works. It's incredible.
Mm-hmm.
Yeah. So as you mentioned, it's almost symmetric. So the downsampling path consists of another 4 convolutional blocks, each of them 2 conv layers, but instead of being followed by a max pooling layer, we introduce something called transposed convolution or up convolutional layer, which is in principle doing the upsampling of our images. So it's basically doing the opposite of the downsampling path. So it's increasing the resolution while decreasing the depth of, so basically decreasing the number of layers. And again, same as with the downsampling path, the number of filters for each consecutive convolutional block is basically equals half of the filters from previous convolutional block. So we're reducing the depth of our feature maps while increasing the resolution. Again, no padding, everything is using valid padding mode. So we're kind of, again, losing some of the border information here. So here we have 104 by 104, and then it's being reduced to 102 by 102, and eventually 100 by 100. So we're losing some of the edge information. One very important thing here is the skip connection that you already mentioned, where we basically concatenating feature maps from corresponding downsampling layers for more precise localization of features detected here. So we're basically concatenating the feature maps from downsampling layers with the upsampled feature maps coming from this upsampling path, which is absolutely mind-blowing here. So, and it's like the final layer of this upsampling path is 1x1 convolutional layer used to map each 64 component feature vector to the desired number of classes. In this case, it's 2 because it's, like I said, cells and background. As for upsampling or the upconvolution or transposed convolution, this goes by many names. And basically what we're doing on this upsampling path, we're replacing, again, coming from the research paper, we're replacing the pooling operators by upsampling operators. And this basically, these layers increase the resolution of the output. So we're downscaling, extracting or learning the context of our images, and then upsampling to the higher resolution output.
Yeah, so just to be clear, that third image, that's a 3x3, and we've upsampled it to a 5x5. And we've just kind of padded zeros all around the original 3x3, and then just run convolution on it as we would do. And then we end up with a 5x5.
Exactly. So there are different strategies for that. You can use different strides. You can use different padding strategies. Like here we have padding only on the border of our feature map. Here we are padding in between the specific pixels. So it's very interesting how this thing works. But the principle is that it takes you from a smaller resolution image into the higher resolution image, and that's how you should understand it. There's a cool repository on GitHub if you would be interested, with much more of these kind of convolutions, both regular convolutions and transposed convolutions, which you can investigate in detail. So,
but just one other quick comment. It's not like max pooling in the sense that it is a parameterized learned upsampling. So we're still learning a convolutional kernel, which will transform from a small domain into a big domain.
Yeah, that's very important to mention, Tim. Yeah, definitely. The kernel, in this case, we're using, in UNet, they use 2x2 kernels for upsampling. These here show us a 3x3 kernel. And like you said, our network will be learning these weights for these kernels. Yeah, and the beauty is that with like most recent tools that we can openly use, like Keras, for example, it's so simple to implement it. I mean, this one here. Yeah, I kind of built it on top of my other implementation of Unit Network. I called it Unit Vanilla, as it's supposed to be most similar to the original research paper. I mean, it's always hard to create a one-to-one exact representation, but in this case, all the shapes, all the sizes are exactly the same as in the original research paper. And as you can see here, we have the downsampling path being created, where each convolutional block is being followed by max pooling, and then the number of filters is being doubled, and we go like this for a specific number of layers. In this case, it's 4 layers, as the same as in the original paper. Then they mentioned that at the end of downsampling path, there is a dropout happening, but it was never specified in which place specifically. Is it, behind this convolution block after the max pooling? Like, it wasn't said exactly. It was mentioned that they're using some dropout in the downsampling path, but wasn't specified exactly where. So yeah, this is basically the conv block that is connecting, that is on the very bottom of the architecture. This is connecting the downsampling path with upsampling path. And then by using the reversed order of downsampling layers, I basically recreate the other arm of my U-shaped network by first decreasing the number of, or decreasing by half number of filters, and using first conv2d transpose, which is part of the Keras framework here. So I'm using conv2d transpose first. Then I'm basically taking the feature maps coming from the downsampling layers and concatenating them with the upsampled on or transposed convoluted upsampled feature maps from upsampling path. The very important thing to mention here is the cropping bit that is happening here, because if we look at the architecture here,
I was going to mention this, Karol, because presumably for this paper they did the cropping thing, and I noticed in your Keras code that you were using the valid padding on the CNNs, but you could presumably use the same, and you could have the same output resolution as what went in, and there wouldn't necessarily be any huge cost to doing that.
Yeah, not at all. And in a minute, I can show you the exact implementation with same padding, which basically gives you the same input size and the same output size.
Amazing. Another comment, though, is that it should be exciting to all of us that we can implement. I mean, Karol has been doing this on many of his projects, but we can all implement UNet in about 20 lines of Keras code. That is just mind-blowing.
Absolutely. Always. It's always mind-blowing. As for the copy or concatenating and cropping and concatenating here with the skip connection, like I said, cropping in case of original unit architecture is very crucial, because here on the left hand side you see that we have a feature map of 136 by 136 by 256, and here on this side we have 104 by 104 by 256, but it's being concatenated. So we first need to take these feature maps and crop it to the to this size, right, to 104 by 104, and that's where we're losing a lot of these border or edge information, right? And that's exactly why they had to go from this large input size image to a bit smaller output segmentation map.
Quick question: did they discuss at all, why they were so adamant on no padding? I mean, why not just use padding, and then at the very end, the image could just have a little shaded area that says this was influenced by padding?
Yeah, so
Could it be a form of augmentation? Because they kind of artificially increase the size of their images by using this mirroring around the edge. So I'm not sure, were they actually losing space on the original images, Karol?
Well, they weren't really losing space, but yes, they could use same padding easily.
But do I understand correctly that they artificially increased the size of their input images by mirroring around where the padding was? So it was almost like a form of augmentation in a weird way. It wasn't like they lost anything.
No, they didn't lose anything. So if we go back to this bit here, can I mark it here? No, I cannot. Or maybe some tools.
So all that stuff around the edge there is kind of like a mirror copy of the stuff inside.
Yes. So this is this area that I'm trying to mark here. This is the actual image that they were provided with. The border outside of this red area is basically what's being extrapolated by mirroring.
So they are doing padding. They're just using mirrored padding.
But they're using padding on the input image. They're not using padding on the convolutional layers.
Yeah, kind of a distinction without a difference, it seems to me. But
well, another thing they did it. Why they did it is to, I guess, get more accurate predictions on the edges or the borders of the image. Because if we would do zero padding here, it wouldn't be as accurate, right? Especially in this kind of architecture that they introduced.
Okay, Karol, we've got 7 minutes to run.
Holy. Okay. Wow. That puts a bit of a pressure on me. Well, it's okay.
It's already been amazing, so don't feel any pressure.
No. As for training, they implemented everything in Caffe, and for Optimizer they used stochastic gradient descent, and like they mentioned here, due to the unpadded convolutions, the output image is smaller, as we witness, than the input by a constant border width, which they are actually padding on the very beginning, in the pre-processing phase. And like they mentioned, to minimize the overhead and make maximum use of the GPU memory, they favor large input tiles, so basically large input size, over large batch size. And they ended up using batch size of a single image. And because they were using SGD, they went with high momentum, 0.99, such that a large number of previously seen training examples would determine the update in the current optimization step of learning.
It's kind of interesting. They had to use a batch size of 1 because the network has so many millions of parameters in it. They would just run out of memory on the GPU.
Yep. And if I remember correctly, it was Titan something. So it had like 6 gigs of RAM at the time.
Wow.
If I'm not mistaken. But single image was all they were able to fit in with this input size and this size of a network. As for the energy function or loss function, they based it on pixel-wise softmax over the final feature map, combined with the cross entropy, standard cross entropy loss function. And a clever thing that they did here is that they introduced this pre-trained weight map here, which was used during the training, and this pre-computed weight map was basically calculated for each ground truth segmentation to kind of compensate the frequency of pixels from certain class, because obviously there were the appearance of pixels from different classes was unbalanced, because there was more. If we look at the images, there was more of these white pixels representing actual cells than the background or border pixels, and so they kind of calculated this pre-computed weight map for each truth segmentation and used it in the final loss function to also not only force the network to better detect both classes, so the border and the cells, but also to work with to enhance the border recognition. So if we go to where's the image? Sorry. Here, right? The borders between cells, they were really focused on making the network or forcing the network to detect those borders as precisely as possible. So they introduced this kind of approach where they penalize the network for not detecting or for merging cells and kind of ignoring the border. And so the border was usually getting higher weights to make it more important.
Yeah, and what's really interesting about this, we don't often see this in neural networks, is that the loss function, as well as being like this kind of softmax per pixel, it has a kind of domain-specific weighting in, because the softmax already gives you a probability, and then we have another probability, and we multiply them together. I mean, actually, this is two, isn't it? Because the WCX is the class imbalance weight thing, and then the bit on the right-hand side is this border separation weight metric. So we're kind of multiplying them all together, and then we're using that as our loss function to optimize on. So that's quite interesting.
Yeah, it is. That was quite clever, and I guess that was a crucial part of the good results they achieved. They also mentioned that the good initialization of weights was extremely important for them. I don't want to go into more details of this, but if you guys are interested, you can definitely read it in more detail. As for data augmentation, they mentioned that the most success they had was with using generating smooth deformations using random displacement vectors, by basically applying a 3x3 grid and kind of displacing the pixels, shifting them, and so on. And that was the most successful bit of augmentation, or the most influential for the training. Oh, and here's the bit talking about dropout layers. So there's a dropout layers at the end of the contracting path perform, which perform further implicit data augmentation, but it's not specifically mentioned where exactly, so it's kind of a mystery. As for the experiments they performed and the challenges, I don't want to go through all of them, but it's worth mentioning that for some of them, like for this, for example, the ISBI cell tracking challenge from 2015, they crushed their opponents by a huge margin, like here by basically 0.1 in IOU metric, and that was huge, and that was the second best, and that was a huge breakthrough.
Okay. We're coming up to time, so just before you go into that, if anyone needs to leave on the call, I just want to say, Karol, this has been absolutely amazing. This is really inspirational. Thanks so much for for explaining to us how semantic segmentation works. Thank you everyone for joining the call. Next week, I think on Tuesday at the same time, we have Katia Mustafina, who's on the call now, and she's going to be talking about the seminal paper that introduced this notion of adversarial examples in convolutional neural networks, because it is possible to add a little bit of random noise to an image and to completely fool a convolutional neural network. So Katia is going to give us the lowdown on that. And apart from that, if anyone can stay on the call, let's keep going and feel free to ask Karol questions. I know Karol's going to talk about a couple of the practical implementations of semantic segmentation he's done. But if you do need to go, thank you very much, and we'll see you next week.
Yes, thank you very much. I'll do a short break here to mention one thing. Discard. Like Tim previously said, I've already used UNet and semantic segmentation models in a couple of the engagements or a couple of projects, and throughout all these projects I came up with some helper tools or utils, reusable utils, which I basically put together into a single package, which is now public on GitHub, and I'll be improving it and adding more and more over time. But this is the base stuff that is already available there, and it's ready to be reused. So if you got any feedback or anything you'd like to share, or some feature requests, please do so. Please check it out and do so. Some of the things that you can see here would be a few of the different model architectures, like a very custom unit that you can modify as you will in different ways. Unit optimized for satellite images, segmentation, or the vanilla unit architecture that can be used as well as some losses that I collected over time, metrics that I'm using for different projects, and some utils mostly for doing stuff like plotting the history of training, or plotting some images, so the original images with maps, with predictions, and so on and so on. It's been very useful to have it in a single library that I can reuse. And with that said, just from my slides perspective, I just wanted to mention one of the projects I did with CSE folks and with Tim specifically. This one was about segmenting out roads from satellite images. And it was very interesting because the data that we received was far away from perfect. So as you can see here on the left-hand side, this first column would be the original image. This would be the ground truth, on top of the original image. So you already can see that we are missing a lot of roads here, but it's not the worst case, trust me. There were worse. And this one over here is the predicted masks through some early stage network that we built. And this is the predicted mask on top of the original image. So as you can see, in some cases, the network, even though we didn't have the perfect data set, the network was trying to kind of do a better job than our ground truth, and it did in most of the cases. Like here, you see the very good examples of network. Even on early stages, outperforming the actual ground truth. And here's some more example of our network being more accurate than the ground truth, doing better job annotating or generating segmentation maps. Here, this is a very, very good example. So again, we got the original image here, the original image with ground truth on top of it, and the predicted mask from our network and predicted mask on top of the original image, which you can clearly see that it's doing far better job than the ground truth that we provided it with. So that was very interesting. We had some mislabeled rows as well. So this network is very, very, very smart in learning good patterns and kind of ignoring the bad annotations, bad patterns that it was provided with. So it's very, very, very cool as well. And in case of this project, we again had to crop the images, even though units can work with really large images and they work perfectly with these high-scale images. Satellite images are usually just too freaking big, so you have to come up with some sort of cropping, sliding window strategy to run efficient predictions and kind of stitch together after running predictions, stitch the predicted masks back together into a single whole map. So that was it. And I don't know, Tim. I think that will be it. I mean, I do have a notebook where I'm using this the package that I come up with to solve the same problem that the original authors were trying to solve. Although I'm not using the vanilla unit architecture, I'm kind of using the improved version of it with
the Karol version.
No, with same padding. I'm not using this no padding technique. I'm following the same padding, so I'm using the same size for input and output image. And here you can see some of the utils or the helper functions in action.
So just quickly, I think it would be fantastic if you could put this notebook on your GitHub as well. But now might be a really, really good time to pause for questions, because we've been depositing information at 1,000,000 miles an hour. And one thing I might hint at, perhaps someone might be interested in knowing about some of the engineering best practice about doing semantic segmentation as well. Because quite often when we're working with, large satellite imagery, for example, we need to segment the satellite imagery into tiles, perform training and inferencing, and then we need to kind of stitch the results back together again. And sometimes, as you notice, the maps that we predicted were noisy, and we need to do post-processing and a whole bunch of stuff. So if I've touched on anything there which is of interest to people, then feel free to ask that question. But over to you, folks.
Yeah, absolutely.
Actually, the same thing is true for digital medical slides, like the cell slides as well, because they come in very big sizes.
Mm-hmm. That's true, Tess. That's very true.
Any questions from folks on the call? This is your chance.
Well, I have a non-technical question. So, if anything, this talk has demonstrated how human ingenuity and whatnot still plays maybe even the dominant role in let's quote unquote machine learning. And that message really gets lost on customers, because frequently I have to kind of remind them that machine learning is not magic learning. We're not at the phase yet where you just say, Starship Enterprise, please make my business more profitable. Okay, I can help you with that. Why do you think it is that message of the extreme importance of people augmenting machine learning, why do you think it is that is so lost?
Well, I think it's partly or largely because of the whole buzzword behind artificial intelligence. And that's why I try to avoid using AI as much as I can, because people basically abuse it. Artificial intelligence is basically floating around the internet, and everyone is attaching to it anything, basically thinking that there's really something magical and intelligent in it. And whereas this is not really an artificial intelligence. It's far away from being artificial intelligence, and it's not. It's always made by humans. It's always human annotators behind these machine learning models and behind the data sets, as you said. So, in my perception, it's because of the abusive usage of the buzzword of artificial intelligence.
I wouldn't use that to diminish, because I think Keith was saying that this is actually ingenious, and it shows the ingenuity of engineers that have come up with an architecture like this. And as we were looking at this U-shaped architecture earlier, the fascinating thing is we don't entirely understand how it works. At best, we are drawing intuitions, but the problem with deep neural networks is we don't entirely understand how they work. So it's kind of genius, but it's also quite opaque at the same time.
One more question here.
Please.
The question is, if you have given a thought on the case where you have multiple images taken from the same object, but in relatively some time difference. For satellite image, it can be like you have the image in different seasons, or for a tissue, a body tissue, it can be through time. Things change, like you get sick, you get better. Is it possible to give multiple images that basically represent the same segmentation, but with minor changes? And sometimes, the degree of noise might be higher, like if there is snow or cloud. Sometimes it's less. Sometimes the contrast is so. Basically, we have more information, but a bit differently. Have you given a thought how it can be incorporated?
That's a really, really good question.
Very good. And my general intuition would be that if we provide more data, in this case, as you mentioned, data for the same, let's say, part of the satellite image, but from different seasons, it should improve the model. It should improve the model to be more general, less specific, right? So in my intuition would be that it would be good. It would improve the model overall, but
it's a fine balance, isn't it? Because on the one hand, if you did provide it with lots of different permutations of weather seasons and so on, the model should learn to ignore the information which is not relevant. But there's always a fine balance, isn't there, in how you sample data to train models, because it's so easy to overfit the context and for the model to learn something that you don't want it to learn. So it could go either way. My intuition would be to, if possible, to perform some post-processing to try and standardize the images as much as possible beforehand, or indeed just to try. But it's one of those things that there are no general rules here. It's really hard to know.
That's a very good question.
Really good question.
Oh, thank you.
But one thing Karol did say before was just remarking on the apparent flexibility of semantic segmentation, flexibility in terms of the input size, in terms of the apparent lack of you don't actually need that many training examples. One thing Karol didn't comment on, by the way, is how you label, how do you create the annotations? Because I know that you've worked on so many applications of this now, and in many cases you've done it by hand, haven't you?
Yeah, I did. Thinking if it's possible for me to.
It's supposed to be done by interns. I don't know.
Always be great. Let me think if I can show something for that. Is there label me here?
So Karol worked on an application where he could remove cranes from cityscape images, and I think Karol got an intern to paint in the cranes on about how many was it? Was it several hundred images?
It was 900, I think.
900, and he
had to do it twice because he had to redo everything with more precise brush. So yeah, it was a nightmare. He did most of this project. Let me try. As for annotation, I mean, there's a bunch of different techniques, bunch of different tools that you can use. One of the tools that I recently used was, let me find it here. Is this it? Maybe. Oh yeah, there it is. So this is one of the tools I've been using for whale tail segmentation.
Yeah, you might recognize this from the famous Kaggle challenge that finished a few months ago. Very, very difficult challenge.
Very difficult indeed. I was trying, in one of my approaches, I was trying to basically extract or get rid of the noise from images by using semantic segmentation to capture the tail of the whale itself for further identification. But yeah, it was a fun project. So in this case, we're doing annotations by hand here using some polygons. So you can get this polygon. You can create new polygons somewhere here, like here, attach it somewhere, and so on. So you can basically mark what you want to mark, add a class for that, like that's Karol, probably, or something, and it's basically generating JSON files for each image with all the polygons and associated classes. But yeah, this is just one of the tools I've been using, if you ever wonder how it works. Yeah, and as you can see, for whale tails, I wasn't that accurate. Discard. Yes. So I wasn't that accurate, but still, UNet is just brilliant because it's able to capture what's really interesting and what's
I mean, this is quite an interesting one to meditate on, because often in computer vision scenarios we think to ourselves that the background information is noisy and wouldn't it work better without, and often that's true actually, because there is a real propensity in vision models to overfit the background, but in this particular case I think removing the background information didn't actually significantly improve the model, did it, Karol?
No, it didn't. I mean, convolutional networks are just super smart, and it was absolutely not necessary to remove the background. It was, I considered it noise, but convolutional networks do not consider it noise. They just are too smart for that, and they get rid of it. They completely ignore it very fast, very quickly. So,
brilliant. Any other questions for the folks on the call?
One more interesting fact, like I said, here I have a notebook, and it's actually part of my Keras unit repository, where I trained the network on the data from ISBI challenge from 2015. And if you look into details here, like the number of examples for training and validation is just like the total data set is 30 images. 512 by 512, which is, you can think nothing, but it's actually enough for this task. So I split it in half in here, and the training half is being augmented heavily, or maybe not that heavily, but somewhat augmented. Here are some visualizations of augmented images.
Did you? How many images how long did you have to train it for to get good results? Because so you started off with 15 images, and then you have an augmentation generator, and then how long?
Can go forever. But so I used batch size of 1 for this. My network architecture was a bit different from the vanilla one, but not that much really. So it ended up having 31 millions of parameters.
Which is a lot.
That's
a huge amount. It's such a dichotomy between 15 training examples with a high resolution and 31 million parameters. That's unheard of.
I know, but it's just
But should you really think of it as 15 samples or like a gazillion samples because every pixel is labeled?
That's kind of interesting. Oh, Tess, what do you do to me? I don't know.
Well, since this is a convolutional network, you have to think of it as many, many samples. I mean, I don't know if per pixel, but every 9 pixels or something is a sample.
Yeah. Yeah, I think this is more crucial, actually, that when you fit that 512 by 512 or whatever size of the images into the input of the model, after the convolutional blocks, you're getting like more and more information being extracted, and you're learning the patterns, the general patterns of recognizing cells in this case. So it's actually much more examples because you're using the smaller patches of this bigger image. So this is like, we shouldn't consider it just 15 examples with data augmentation. It's far more than that.
Well, there's kind of two things, because Tess was saying in some sense, it's, what's 512 squared? It's a huge number of pixels. But also there's the sense of if there's 15 unique examples and you augment it to infinity. We were having this conversation with Keith earlier. I mean, to what extent is augmenting providing new information? I mean, for us, it's not providing any information. And for the network, it's providing a lot of new information because it's learning completely new patterns. It's probably not even reusing internal patterns, for different rotations, for example. So it's kind of philosophical. And it's another example of where we don't completely understand how neural networks work.
Yeah, well, I think Tess made a very good point on that. These millions or gazillions of single pixels that are being labeled here, because we look at this as a whole image, but the network is considering each pixel and painting it with specific class. So yeah, this is.
Well, it's kind of interesting because as Keith said, it's shining these convolutional filters over the entire map, but also because of the low batch size, it's only generating one weight update on the parameters per epoch, right? So it's kind of not per epoch, but per batch. So yeah, I don't know.
It's confusing. But the interesting part is that even with this, not that great augmentation and somewhat lazy implementation, after training the model for 10 epochs with 100 steps per epoch, so basically 100 images went through the network per epoch. So total of 1,000 images.
Yeah, so that's 1,000 images.
Yeah, I went through the network through the whole training, and it got up to, on validation IOU, it got up to 80.83 or 84 almost. Right.
Could you show us the convergence graph on loss? Yeah, so this is really interesting. So it's kind of, it's not even overfitting, not necessarily.
No.
You could have just kept training that for a long time.
Yeah, that's the intuition behind it, and as the original authors behind the unit mentioned, they trained their models for about 10 hours before running predictions.
And just for the benefit of the folks on the call, so if we see a divergence of validation loss and train loss, then we would say it's overfitting. But if they're both going down in the same direction, then keep training. Keep training.
Yeah, all of them show up, right? On one page. If that is 1,000, then it will be messy, correct? Yeah, so it should be different images. So for that purpose, I have made like diagrams. So in some.
Was that
I'm not sure if that was a question or that was
discussion.
Background chat.
Well, got me
Any
quite interested.
questions, folks? This is Karol. This has been absolutely fascinating. I think just going from the theory of the paper and turning it into a practical reality that all of us can actually, take something useful from. Because what is so interesting about this is it's really, really fascinating, and it's not that difficult to implement. All of us can implement this on our customer projects. You don't need that much training data to make it work. It works really well. It's something that all of us can use in our kind of computer vision toolbox. So this has been a fantastic kind of end-to-end discussion, I think, from the original research paper and how we can implement it in our projects. So Karol, thank you so much. That this is, honestly, you've raised the bar so high. This has been a wonderful paper review call. Really, really appreciate you putting the work in. And I guess we might as well wrap up if there's no more questions, and we'll see you all on Tuesday evening for Katya's talk on the adversarial examples.
One really fast question. Where's a good website to look up the current state-of-the-art network for various tasks, like UNet for segmentation, ResNet or whatever for this?
Paperswithcode.com.
Oh yeah, this one.
Let me just check that. But what that does is it links you the GitHub repo, which has the best implementation for, and Karol will get it up. So whether it's natural language processing or computer vision, you can find the state of the art implementation with the code. There's a new page on here, Karol, where it even breaks down by, or maybe this is it, but is it NLP or is it computer vision and is it semantic segmentation?
You can go by greatest and go like TensorFlow, Cafe, Detectron.
Are you in the core test? Do you remember this page where it breaks it down by the type of? There's like little icons for all the different predictive tasks. Click on Browse State of the Art. Is that it?
Oh yeah.
Yeah, there you go. There you go. So semantic segmentation. So if we click on that, you'll see UNet in there somewhere, and you'll see all of the state of the art results. Those are data sets, aren't they?
Data sets and the best methods for this data set.
Yeah. So it looks like this Deep Lab v3 with the exception CNN architecture came from Francois Chalet, and it has this depth-wise separable convolution trick in, which hopefully we'll do a paper review call on soon.
This is brilliant. So yeah, paperswithcode.com.
Yeah, that's where it's at.
Cool, thanks.
All right. Would that be it, Tim?
I think so. It's been emotional. Thanks again, Karol. It's honestly really, really fantastic call. It's been absolutely amazing. So thank you so much, Karol. And we'll see you next week, everyone.
Yes. Thank you very much, everyone. Thank you for being here. Take care.